let's look at some examples here of exponential growth and decay. So here we have a lab experiment starts with a population of 4,000 bacteria that is growing with a relative growth rate of 7.2% per hour. We want to find the population and its rate of change after 3 hours. And then, how long will it be until the population reaches 18,000? Alright, so let's start first by writing down a function for its population. Okay? So, remember that this kind of model is one of those exponential growth models. Right? So we need to fill in the function a of t equals c e to the kt. All right? So how do we find all these things? Well, k is that 7.2%, which we changed to a decimal, so 0.072. Now, how about this c, though? How do we deal with c? Well, let's plug in this k and see, how it works out. All right, so a of t will be c e to the 0.072t. And since the initial population is 4,000, we know that a of 0 has to be c e to the 0.072 times 0. And that's just c, right? Because this here, this is 1. And this is always going to be true. So this c value here, this is the initial population. All right? And if you remember, we had something like that for the continuously compounded interest. Okay? Anyway, so this tells us a of t is 4,000. Oh, sorry, I should mention. Let me move this up a little bit. I should mention here that this quantity is equal to 4,000. A of 0, the initial population, is 4,000. Okay, so a of t is 4,000 4,000 e to the 0.072 t. Right? All right, so there's the population at, right, this here is the population after t hours. Okay. Now, so that's this part done. Let's find its rate of change after 3 hours. Okay, so there we're looking for a prime of 3, which means we want a prime of t first. So it'll be 4,000 e to the 0.072t times 0.072. All right, so I seem to have misplaced my calculator here. All right, well, let's pull this up on the PC here. So we want 4,000 times 0.072. Right. So this simplifies to 288 e to the 0.072t. Right. And so the rate of growth after 3 hours would be a prime of t, which is 288 e to the 0.072 times 3. And we compute this number. All right, so let's see. We have 288 times. Okay, we'll do it this way then. 0.072 times 3. Right. Then we're going to multiply that by 288. Right? So this number here is about 357.437. Okay? So what does that mean? What does this mean in terms of the rate of growth? What does this 357 tell us? Well, it tells us that after 3 hours, the population is increasing at a rate of 357, let's say at a rate of about 357.437 bacteria per hour. Right, so that answers the next part of this question. All right. Now the last part of this question is asking how long until the population reaches 18,000. How do we figure that quantity out? Well, to figure that out, we essentially want to take our function up here that we solve for. So this thing up here, we're going to duplicate this, right? This stuff right here, what we want to do is take that and set it equal to 18,000. Because that's what we want to know, right? After what time will this equal 18,000? So we set it equal to 18,000, and now we need to solve for t. So divide both sides by 4,000, and we have 4.5 equals e to the 0.072t. Now, to start solving for t, we need to remember some of our properties of logarithms here. In order to get things out of the exponent here, we have to be able to cancel this out. So let's apply ln to both sides. 4.5 ln of 4.5 equals, when we apply ln to this side, the ln and the e cancel, and we're left with that. And so t is going to be ln of 4.5 divided by 0.072. Right? I should actually have up here some squiggly equal signs for approximate. Right, so let's go ahead and compute this. So we want ln. So we want. Okay, so 4.5. We want ln of 4.5, and then we want to divide that by 0.072. Right? So that's about 20.890. Right, so it will take about 20.89 years. Oh, sorry, not years, hours. To reach a population of 18,000. All right, and that's the answer to the final part. All right, so this here is an example of what we call exponential growth. Here, the quantity we're measuring is growing over time. All right, and that growth is actually reflected here in the value of k. If k is positive, this means growth. Okay? But now, what does decay look like? Well, we got another example here, just to show that off. Okay, so here we have an example where the half-life of the radioactive material cesium-137 is 30 years. And let's suppose we start with a 100 milligram sample. And then we have a few things we want to do. Write a formula that gives the mass after T years, how much remains after 100 years, how long will, or after how long will only 1 milligram remain, and at what rate is the mass decreasing after 100 years. Right? So, let's look at this. All right. So, let's start out by writing this function down. Now, you might notice we're missing some information now. Right? Let's write down what we can. All right. So, for part A, we know that C, the initial amount, right, in A of T, the initial amount is 100 milligrams, so we're going to put 100 here. E, but we don't know what K is. We don't actually know what K is. So how can we find K here? Well, this is where it comes in to know what the half-life is. The half-life means that after 30 years, whatever you started with, you'll have half of that mass left over. So, what this means then is that A of 30, this equals 50, right? So after 30 years, we have 50 milligrams left. All right, but if we plug 30 in up here, this is 100 e to the k times 30. Okay, so what are we looking to solve here? Well, if we, again, focus on the equation here, we can start by dividing both sides by 100. I'm going to write this as e to the 30k over here. All right, then we can take ln of both sides. Okay, and then we can find that k is going to be ln of 1/2 over 30. Okay, now something you may or may not know from, say, a chemistry class or biology class or something is there's kind of like a log or ln2 rule. Usually you would write this as negative ln of 2 over 30. So negative ln of 2 divided by the half-life gives you the k value here. Or normally you would say ln of 2 over 30 is the rate of decay, and then you would add in the negative sign. But let's go ahead and compute this. All right, I'll let you sort of try and remember or think about why ln of 1/2 is equal to negative ln of 2. I'll let you think about that. All right, so let's go ahead and compute this. So ln of 1/2 divided by 30. All right, and this is approximately negative 0.023. All right, so think about what we're sort of looking at here. This k value is negative. So when k is less than 0, this is the case of exponential decay. Right? In this particular example, it's what we would refer to as radioactive decay because of the application. But mathematically, this is what we call exponential decay, when the k value is negative. Okay? All right. So we can now write down our function for the amount of mass left over. Okay? And there we go. This here is our function for the mass left over after t years. All right, so that's part A. Part B is asking how much remains after 100 years. Well, all that's asking us for is, what is A of 100? Right, so this is 100, e to the negative 0.023t, or sorry, times 100. Right, so we just compute that. Right? So, sorry, e to the e raised to the negative 2.3 power. That's not right. E raised to the negative 2.3 power. There we go. Right? And then we multiply that by 100. Right, so that's about 10.026. Okay, so this says that after 100 years, 10.026 milligrams remain. Okay. So that's part B. Part C is asking us, after how long will only 1 milligram remain? Right. So at this point, it's kind of stuff we've already done, right? Right. So here, we're now asking A of t, this is 100, e to the negative 0.023t. And if we want only 1 milligram left, set this equal to 1. And now we want to solve this equation for t. Right? Well, again, start out by dividing both sides by 100. And then we take ln of both sides so that the e's cancel over here. And then solve for t. We have ln of 1 over 100 divided by negative 0.023. Right. So let's see here. So ln of 1 over 100. And then we want to divide that by negative 0.023. And that'll give us about 200.225. Okay. So we would say, let me learn how to write here. It will take about 200.225 years for the mass to decay to 1 milligram. Okay. And that's quite a long time, right? And that's kind of the principle behind like carbon dating and radioactive dating and stuff like that. So hopefully you'll learn more about that in another class. Right. The last thing we need is, at what rate is the mass decreasing after 100 years? Right. So this one's pretty straightforward. Right, just like last time, we start by writing our function. Right, if we want to know at what rate is it decreasing, well, we want to take the derivative. All right, so this will turn out to be I'll let you verify this, but it'll be negative 2.3 e to the negative 0.023 t. Right, that's the simplified version. And then we're looking for a prime of 100, which is negative 2.3 e to the negative 2.3. Right, so e to the negative 2.3 times negative 2.3. Right, so what we get here is approximately negative 0.231. All right, so what does this mean? Right, so since the rate of change is negative, that means the mass is going down, which is what you expect. The way we interpret this, though, is we say that the mass is decreasing at a rate of 0.231 milligrams per year after 100 years. Right? Now, why do we change this to a positive number here? You might legitimately wonder. And that all has to do with the fact that we use the word decreasing. Since this is saying that the mass is decreasing, then we're already sort of implying that the rate of change is negative. So now we just want to give the quantity of that rate of change. Right? If that hopefully makes sense. Right? And then that's that. That is exponential growth and decay. So hopefully those examples made sense and we went through them carefully enough. And we'll see you for the next ones.